So, have a very good morning to all. So, today I shall take a class on deflection in beams, particularly using energy methods. And truly speaking, there are so many methods available to find the deflection in beams. So, let us first understand what is meant by deflection, why we are going to study that, in what aspect it is so important for us. It is generally observed that any beam, when it is externally loaded, it will deflect from its original position. For example, let us take a cantilever beam. It is the external load applied. So under the external load, the beam will deflect. And this is the amount of deflection. Before load is applied, this is the original position and this is the deflected position after load is applied. And this amount of deflection depends upon what is the area of cross section of the beam as well as the bending moment of the beam at any section. And for any design engineer, there are two important design criteria. One is the strength criteria of the beam, other is the stiffness criteria of the beam. According to the strength criteria, we are interested in calculating how the beam resists the shear force and the bending moment. In other words, how the beam is resisting to the shear stresses and bending stresses produced by the load. And according to the stiffness criteria, which is also equally important, we have to determine how the beam is adequately stiff to resist the deflection. In other words, the beam should be stiff enough to produce deflection within a permissible limit. And if the deflection produced is beyond the permissible limit, then the failure will happen. So that's why the study of a deflection in beams is very, very important to us. Again, how to determine the deflection in a beam due to external load? And we have so many methods are there. Your conventional method or classical methods, which include double integration method, Maclaurin's method, moment area method. And another method is also very new method is there, that is called the energy methods. And these energy methods also there are many. And there are strain energy method, Castellian theorem, virtual work method, and your Maxwell's reciprocal theorem, also theorem of minimum potential energies. And today class, our focus is mainly on some energy methods is there. And before start, so I want to explain these deflection beams, what is meant by beam. We know there are two mechanical members, one is bar, other is beam. What is bar? Bar means it is a mechanical member which is applied with the axial loads, due to which there is elongation or contraction. That means this is the example of a bar. Only this is your axial load P and P. P and P. Either the axial load acts as a pull or is a push. And what is beam? Means it is a mechanical member which is applied with the transverse loads. Applied with the transverse loads. Like that. So, these are some learning objectives. So what we learn by studying this deflection in beams, there are so many learning objectives are there. Here we have to study what is the strain energy produced in a deflected beam. And second learning objective is how to find out the deflection produced in the beam due to external load. Then we have to discuss some energy methods by applying which you can calculate the deflection in a beam. And the two important methods I shall tell you today. One is strain energy method, other is your Castellan theorem. Then some basic terminology let us talk about. You remember that there are basically two methods are there basically. One is a vector method, other is a scalar method. By definition, vector is a physical quantity which has a magnitude and a direction, and by definition scalar is a physical quantity which has a magnitude only. And it is always easy for anyone to deal with any scalar method. And we know energy in any form, whether it is a kinetic energy or a potential energy or a chemical energy or strain energy, any form is a scalar quantity, and that scalar approach we are using here. Then what is meant by external work? And this conceptual work is, we know when force is applied, when a load is applied, the body will deform. That means this is the load, and load produces deformation. Let a load is P and deformation is equal to delta. And in all practical calculation, we have to assume that this load is gradually applied. For all practical purposes, we have to assume that. Gradually applied means load is applied to its full value from 0 to P. It is not suddenly applied. And due to which the deflection delta is produced. And we can now plot a load and a deflection curve. Load is taken along the y-axis and deformation or deflection taken along the x-axis. And when the body is loaded within the elastic limit, this graph is a straight line. So this is your P, and this is the amount of deformation produced. And we are getting an area under this load deflection diagram. And by your elementary knowledge, we know the area under a load displacement diagram is nothing but your work done. So what is work done? Work done is equal to, we know, area of this load diagram. And area of the triangle. What is the area of the triangle? It is half into delta into W. That means work done is equal to half W into delta. Right? Or half P into delta here. Half P into delta, because you have taken load as P. So then what is the elastic strain energy? Elastic means always the body is expected to be loaded within the elastic limit, not beyond that. It is always desirable. And strain energy means we know when a load is applied, body will deform. Load produces deformation. And some internal process will be produced, will be developed within the body to resist that external load. In this way, the internal process produced within the body will do some internal work. And this internal work will be stored as energy within the body. And that stored energy within the body is known as strain energy. Why it is called strain energy? Because energy is stored due to straining action of the body. That's why it is called strain energy. And then what is the energy balance? Energy balance is nothing but, it is your law of conservation of energy, which says that energy is not created nor destroyed, right? Only it can be transformed one form to another form. So work done is one form of energy. So when it is done on the body, that will be stored within the body as strain energy. And this concept of energy balance says that work done is equal to strain energy. So this is the elastic strain energy. Already I have explained to that. So when work is done, body will be deformed, and due to some work done on the body, so that what done on the body will be stored as energy within the body is known as strain energy. Then strain energy under different loads. And there are so many types of loads acting on a bar or a beam. So let us discuss briefly what are the expressions for strain energy expression, and this strain energy expression already have studied in your previous semester MOS 1. And if it is the axial load, this is sigma and sigma, then the strain energy is equal to integration of 0 to L, it is sigma square by 2E into dV. Due to axial stress. And then similarly, due to simple shear, instead of normal stress, it is a shear stress. Similarly, due to bending, and we know that when a beam is loaded by transverse load, the beam will bend. Let at any section, this is your XX, at a distance X, and this is your M. And this M is nothing but is equal to minus P into X. And this bending moment produces strain energy on the beam. And the strain energy produced due to bending moment is given by m square dx by 2EI integration from 0 to L, where L is the length of the beam. Similarly, when the torque is applied, you have studied in the torsion chapter, when torque is applied, only the thing is your M is replaced by torque T, and E is the Young's modulus, here is shear modulus, I is the rectangular MI, and J is the polar MI here. Get it? Then let us discuss some energy methods here. Already I have told you there are so many energy methods are there, but here as per your curriculum and syllabus, only we have to discuss with it two methods. One is strain energy method, other is Castigliane's theorem. So let us now come to what is meant by strain energy method. And by law of conservation of energy, we know that work done is equal to strain energy stored. That is, work done is equal to half P into delta, and this is U is the strain energy stored. So we are getting a final relation is equal to half of P into delta. So if you are able to calculate the strain energy U from this expression, you can calculate what is the value of delta, which is our objective. So now let us learn how to calculate the strain energy now. So let us take a problem is here, numerical problem is here. Suppose this is a cantilever beam, and you know cantilever beam is a beam whose one end is fixed, other end is free, and a point load P is applied at the free end, and let the span of the beam is equal to L. And here first we have to learn how to calculate what is the strain energy value. U is the strain energy. And for this, so you have to choose any section on the beam. Let the section be at a distance x from the free end. Then M is equal to bending moment at any section xx, and this value is equal to minus P into x. Then U is equal to strain energy, which is, we know the formula is integration of 0 to L m square dx by 2EI. So this is the strain energy formula for due to bending moment. And this is equal to 0 to L, and m is minus px into dx by 2ei. Just I am putting the value of m here. And this is equal to p square, take it out, it is constant, 2ei, take it out, it is 0 to L x square dx. This is equal to p square by 2ei into s cube by 3, 0 to L. So this is equal to p square by 2ei into L cube by 3. So from which it is p square L cube by 6ei. And this is your answer for you. And this is a simple problem for you. We can learn here how to calculate the strain energy stored in the beam due to external loading. So for more clarity, let us take another case. For another case, I am taking another case study. Here I have considered the point load. Let us take a UDL, uniformly distributed load. This is uniformly distributed load, A and B. This is your L. And the intensity of the UDL is, say, Q. And this is Q per unit length. And again the same problem is how to calculate the strain energy U. Then the same approach is here. Let us take any section XX, which is at a distance of x from the free end. As x is made up from here, x is equal to 0 and x is equal to L here. So here calculate what the M value. M value is equal to Bm, bending moment, at section XX, and this value is nothing but your minus Qx into x by 2. And how it comes minus Qx into x by 2, let me explain. Let us take this length of the beam here separately. This is a B end, this is your section XX, and this is the distance x. Per unit length it is Q, and as spread over length x, it is Q into x. And this Q into x is the equivalent point load. Q into x is the equivalent point load. And equivalent point load should be acting at the middle of the portion. That means this is x by 2 and this portion is x by 2. That means this distributed load is now replaced by the point load. I think this concept you know your most one. And here M value is equal to, by definition, moment is equal to force into the perpendicular distance. You are taking moment here. So this is the minus of Q x square by 2. Then we have to calculate what is the strain energy U. So strain energy U is equal to 0 to L m square dx by 2ei. And here 0 to L m value is equal to minus Q x square by 2 squaring into dx by 2ei. So by solving that is Q square taken out and it is 8ei, integration 0 to L, it is x fourth into dx. And this is equal to Q square by 8ei into, it is, if you integrate this is nothing but L to the power 5 by 5. And from which the value is Q square L 5 by 40 ei, and this is your answer. So this is the way I have given you two examples of how to calculate the strain energy in a loaded beam. But our important objective is what? Our important objective is to find the deflection. So how to find the deflection using this strain energy concept? So already we have discussed about strain energy method. So strain energy method. This is used to determine the deflection. And we know this is U is nothing but is a half P into delta. And what is P? P, the external load is applied on the beam, due to which that is the deflection amount is delta. And this is the due to deformation, U is the strain energy stored. And we have to use this equation, then we shall find out what is the delta value here. So this delta value can be found out. And we know that P is the given load, and U how to calculate already you have learnt, and from which you can get the value of delta by using this equation. So now let us take a numerical problem here. So problem number 3. Suppose this is a cantilever beam and this is the load P. It is span is L. And as the external load is applied at the free end, so the beam will now deflect from the original straight position. So this is the deflected end. That means AB will be deflected to AB dash. That means the free end is deflected from B to B dash, and that B to B dash is in nothing but it is the vertical deflection at point B. And our objective is how to find out that delta. So how to calculate that? And for this we have to use U is equal to half P into delta. But what is U? And we know U is equal to, you take any section XX at a distance x from the free end. And here M is the bending moment at section XX, at section, and which is nothing but minus P into X. Why it is minus? Because it is your hugging moment and concave side is downward. And U value is equal to, it is m square dx by 2ei integration from 0 to L. And this value is equal to 0 to L, it is minus px into square dx by 2ei. And this value is equal to p square by 2ei into integration from 0 to L x square dx. So from which U is equal to p square by 2ei into L cube by 3. So from where U value is equal to p square L cube by 6ei. So this is the already we have calculated. We calculated the what is U value. Then by strain energy method. By strain energy method we know U is equal to half P into delta and subscript is B. And this subscript B represents that delta means deflection at point B. And here U value already we have calculated, it is P square L cube by 6ei is equal to half P into delta B. And by solving that, delta B is equal to P L cube by 3ei. And this is your answer for you. This is the required answer. And I want to clarify one point. The same result also can be done by your classical method, any traditional method, but it will take a lot of time. But by employing the energy method, I think we are getting the solution with the minimum labor and minimum time. So this is the benefit in applying the energy method. So we learned to one case. Let us take another case how to solve that. Let us take another problem, how to apply the strain energy method to obtain the deflection. So let us take another type of beam. So let us take a simply supported beam. Simply supported beam, AB. And here P is the applied load, and it is applied at the center of the beam. This is your L, and this is your L by 2, and this is your L by 2. And load is applied at the mid span of the beam. Then what will happen? Due to this downward load, definitely the straight beam initially will deflect now. It will deflect downward. And the maximum deflection will be where? At the point where load is applied. So our objective is how to calculate the deflection at point C. This is your objective. Then what to do? First we have to calculate the strain energy, then we have to use the U is equal to half P into delta. So first part is how to get a U value. And before that, let RA and RB is the support reactions. As this is P is applied centrally, so reaction will be just half and half because it is applied centrally. So this is P by 2 and this is P by 2. It is P by 2. Then you take any section XX here, any section XX, and this is your distance X from the free end. Then your M is equal to bending moment at any section XX. And this value is equal to, you see, this is the portion I am taking. This is the portion I am taking. This is your section XX, and this is your end A. This is your reaction RA is equal to P by 2, and this is equal to your X. And the bending moment at this point is equal to, we know by definition, moment is equal to force into the perpendicular distance. But it will bend upward, and it gives a sagging moment, means the concave side is upward. That is your plus P by 2 into X. This is the bending moment. Right? And then your total U value is equal to, M square dx by 2EI from A to C whole into 2. And U is the total strain energy. Total strain energy means it is from A to B for the entire span. But as C is the midpoint, it is L by 2 and L by 2. So if we can calculate strain energy of half of the portion, then for this portion the strain energy will be the same value. That's why we need to multiply here 2, because we are taking from A to C. And this is equal to, A value is equal to how much? X is equal to 0, because as X is measured from here, X is equal to 0. At here, X is equal to how much? L by 2. It is L by 2. And M value is equal to, this is P by 2 X into squaring into dx by 2EI, and from which U value is equal to P square by 4, taken it out, 4 and is 2, 8EI, integration from 0 to L by 2, and here 2 is there also, 2 is there, and here is 4, and this is x square dx. This is equal to P square by 4EI into this is S cube by 3 from 0 to L by 2. And this is equal to your P square by 4EI into your 1 by 3 into L cube by 8. So from which it is P square L cube, it is a 96 EI. This is equation number 1. So we calculated what is the U value here. Then our main objective is what is that? To find the deflection delta at the center C, and we have to apply strain energy method. So by applying strain energy method, we know U is equal to half P into delta C, and U value is equal to P square LQ by 96 EI is equal to half P into delta C. By solving that, delta C is equal to PLQ by 48 EI, and this is your answer for you. So this is the way how we are applying the strain energy method to determine the deflection at any point. So let me see how many of you have understood this. Actually, already I have told you that I have to discuss two methods. One is strain energy method, other is Castiglione theorem. And we finished strain energy method, how to find the deflection. Then very shortly we shall go to the second method, that is the Castiglione theorem. But I want to know, do you have any confusion is here in understanding this? If any confusion, it is highly welcome for you to ask anything here. Do you have anything to ask me? Anything? Do you understood this?
Yes, sir.
Nothing to ask here? So can I go to the second method?
Yes, sir.
Yes, let us go to the second method for you. And the second method is nothing but your Castiglione theorem. And remember that this method is very important tool in your study of engineering. And its development is very new in the 19th century, you see. And this theorem is developed by an Italian civil engineer. A name is Albert Castiglione, the Italian civil engineer who has developed this theorem while studying the structural analysis in the year 1879. So this is a recent development and it's very efficient tool to find the deflection. So what is Castiglione theorem? So the statement is like that. Suppose this is a simply supported beam. This is a beam is here, A and B. So many loads are acting, W1, W2, W3, say up to Wn. And they are acting at point, say, point 1, point 2, point 3, point 4. Then under the action of these transverse loads, the beam will now deflect down. So this is the deflection curve after load is applied. And here under the point 1, deflection is delta 1. Correspondingly, this is delta 2, this is delta 3, and this is your delta. If n point is there, this is your delta n. And n means it is signifies any number of loads can apply, not only limited to 4 loads, any number of loads can apply. So how to get this? Then by Castiglione theorem, what it says, delta in general is equal to, it is dou u by dou w. Dou u by dou w. What is that? Dou we are using means it is a partial derivative. Of what? With this u, strain energy, with respect to load w. So statement is like this, the partial derivative of the total strain energy with respect to any load at a point is equal to the deflection at the point where load is applied. And mathematically, this deflection is nothing but summation of your partial derivative of strain energy with respect to the load applied. And this is in general. And if you go to in particular, you will go in particular, here delta 1 is equal to dou u by dou w1 and delta 2 is equal to dou u by dou w2. Similarly, dou delta n value is equal to dou u by dou wn. And where U is the total strain energy under the action of several loads. So it is very simple to use. So now let us apply this Caston theorem, how to get the deflection. Now let us take another problem for you. The problem inside is 5. Problem number 5. And let us take the same example here. This is your load is W. And beam is AB, span is L. And under the action of the load W, it will bend to B dash. And this is the amount of a delta B. And using Castigliane's theorem, so what is your delta B? And already we have find it out by using the strain energy method. This value is nothing but your W LQ by, what is that? 3I. Already you have done it by strain energy method. By strain energy method. Right? We know your capital U is equal to total strain energy. Total energy. And already we have derived it is W square LQ by 6EI. Do you agree? Your problem number 1 already have derived for this cantilever beam what is the total strain energy. You can refer that. And by Castigliane theorem, by Castigliane theorem, your delta B is equal to, we know, partial derivative of, what is that? With respect to W. And this is nothing but dou by dou W, and capital U already you have derived. This is W square LQ by 6EI. And here you treat as a taking the partial derivative with respect to W. So W is the variable and any other term are the constant terms. And as the W square is there, what is the derivative of W square? It is 2W and 2 and 6E. What is that? Numerator is 3. That means it is W LQ by 3EI. And this is your answer. This is your answer for you. And you see, the same thing is there. Same result is there. Again, I shall tell you another way how to apply Castigliane theorem. I shall tell you how to, but it is another way to use the Castigliane theorem. So, another expression for Castigliane's theorem. And we know delta is equal to dou U by how much? Dou W. This is equal to written as dou U by dou M into dou M by dou W. Just rearranging. And this is equal to dou by dou M and U. U is nothing but integration of 0 to L M square dx by 2EI into dou M by dou W. Get it? So, this is equal to, and here in respect to M, and here M square is there. So, what is the derivative? It is 2M, and these 2 and these 2 will get cancelled. So, what remains? It is 0 to L M dx by EI into dou M by dou W. So, from which you can find out delta value is equal to 1 by EI, it is a constant you can taken out, and 0 to L, it is M into dou M by dou W into dx. This is the alternate expression for Castellan theorem. You see, try to remember that actually this new expression has been derived from here only. So you are free to apply either this expression or this expression. But what is the advantage here, you see? By using this expression, what we have done in the previous problem, first you have to calculate separately what is the u value. But in this new expression, which is the same as this, but here u term is not there. That means you need not require to calculate the strain energy separately. And for calculating u here, you are calculating m. So only that m calculation is enough to find out the deflection. So definitely, so this new expression is very advantageous over this earlier expression. So let us now take the same problem, how I am using this expression, you see. So again take the same problem, let us revisit the same problem again, and let us prove how easy this new method is there. This is the cantilever beam, this is the load W, and this is L, and it will deflect like that. B dash, this is your delta B, and we require what is the delta B value. What is this value is there? And let us take any section here XX at a distance X. And what is M here? M, BM at the any section XX. You take the right side, this is W into X. As it is producing sagging, hugging moment, it is minus W into X. So M we calculated. Then next term is dou M by dou W. It is dou M by dou W is nothing but you take the derivative with respect to W here. It is minus X. Then what is the delta B? Delta B is equal to, use this equation. This is 1 by EI into 0 to L, M into dou M by dou W into dx. Just write the expression there. And from which it is 1 by EI, 0 to L, and M value is nothing but minus Wx into, it is minus X into dx. And from which your delta B value is equal to 1 by your W taken out, W by EI, 0 to L, it is x square dx. And this is equal to W by EI into this is LQ by 3. So this is equal to WLQ by 3EI, and this is your answer. And this is the same as before. Same as before. Get it? But if you compare the time and labor, definitely this way is very advantageous for you. Why? Because by this method you are not going to calculate U separately. Simply you are calculating the bending moment, and this especially in terms of what is that? Bending moment only. So definitely this method is very advantageous for you. Get it? Then the last part of the session is, this is your fictitious load in Castellan theorem. What is meant by fictitious load? Fictitious load means, remember that, what is my fictitious load? Fictitious load means it is imaginary load. Imaginary load means not actual load. Not actual load. And this is sometimes this is called dummy load. Sometimes it's called dummy load. And what is the necessity to introduce dummy load? Remember that Castellan theorem can be used only when a point load is applied at a particular point. Castellan theorem is used to find the deflection at a point, but it is necessary that a point load should be applied at the point where deflection is required. Suppose you are calculating the deflection at B. At point B, there is a point load is there. Either it is P or it is W. But more often you will find that some situation may arise for you that you require a deflection at a particular point, but where a point load is not there. And in that situation, you have to introduce a dummy load, a imaginary load. That means, for example, so let us take a cantilever beam here and loaded with the Q per unit length, and this is A and B, and length is equal to L. Then what will happen? Then under the action of the load, this will bend. This will bend. It will go to B dash, and this is the amount of deflection. And we require what is the deflection there. And you see here, in ordinary sense, your Castell's theorem you cannot apply here, because it is required to apply for Castell's theorem, a point load should be applied at which the deflection is required. I require the deflection at point B, delta B, but is there any point load at point B? No. So that's why ordinarily your Castell's theorem will fail. But Castell's theorem is not applied in particular, it is general theorem. It can be applied to any situation. And to overcome this difficulty, so you have to introduce a dummy point load. Where the deflection is required. Where deflection is required? At point B. So at point B, you introduce a dummy load, that is your W. And here W is nothing but, it is called your dummy load. And remember that it is, of course, it is completely imaginary. It is your imagination, it is your thought, and it is not actual load. But be careful that only to facilitate the calculation, we are introducing this dummy load W, but in the final result or during integration, you have to put that W value is equal to 0, because that W is not a actual load. Get it? So how to solve now? And here, let us take same approach, let us take any section XX, and it is at a distance of X, and what is the M here? And M is equal to minus your W into L minus Q X square by 2. And this is the moment produced due to the point load, force into distance, and this is the negative moment produced due to the applied UDL Q. And then dou M by dou W, because we require the deflection at point B, point load is W, so this value is nothing but it is minus L only, and all other quantities are simply constants. Then how to calculate delta B? By Castigliane's theorem, we know delta B is equal to 1 by EI, your M into dou M by dou W into dx from 0 to L. The same expression I am taking, and here this is 1 by EI from 0 to L, and M value is equal to minus WL minus Q X square by 2, and this is minus L into dx. And once this quantity comes in the integration, you can take this quantity is equal to what is 0. Because you remember that this W is not actual load. That's why I have shown by dotted line, not by solid line. It is imaginary load. Its value practically nothing. That's why once it enters in the integration, so you make it 0. So what this value is? This is minus or minus is plus. It is QL by 2EI. And this is equal to 0 to L. It is X square into dx. And this value is equal to QL by 2EI into, this is your SQ by 3 from 0 to L. And this is equal to QL by 2EI into LQ by 3. And this is nothing but your QL4 by 6EI. And this is your answer for you. This is your answer for you. So this is the way how we are calculating the deflection. So this is all about your Castleton theorem. We take a direct problem, so directly can be applied, and some situation may arise where no point load is acting at the point where deflection is desired, and for that situation you have to introduce a dummy load or imaginary load. It is a fictitious load, and by introducing fictitious load we are getting the result here. So this class is over, and what we learnt here. The learning outcomes is the students, by studying this session, by studying this chapter, students can learn about how to determine the strain energy. We have done few problems here. Also, how to apply the energy method to determine the deflection. Energy method means it. Already studied, we learned two methods. One is strain energy method, other is Castleton theorem, and how they are used to find the deflection there. Then how to solve your problems involving your deflection of a statically determinate beam and statically indeterminate beam. Of course, we have taken few statically determinate beam, but also this problem can be conveniently extended to solve any indeterminate beam. So let me finish what is statically determinate beam and what is statically indeterminate beam. Statically determinate means the problem can be solved by use of equations of a static equilibrium, that is sigma x is equal to 0 and sigma y is equal to 0 and sigma m is equal to 0. If these three equations are enough to solve the problem, it is called statically determinate problem. But more often you will find that there are more constraints than number of equations, and more reactive forces are there which are unknowns. In that case, by just applying three equations equilibrium are not enough to solve the number of unknowns. That means we have to use some compatibility equation in addition to the equilibrium equations. And those equations are known as, those beams are known as statically indeterminate beam. And this is the summary of this session. What is the summary? Here we learnt, and this lecture is completely devoted to the study of strain energy and to determine the deflection in the beam subject to external loading. How we are getting that? How we are calculating that? So this is the summary of this, and this is thanks for you. And can I have few questions from your side? So now we finished two methods, very important methods we studied here today. So can I welcome few questions from few queries, from few confusions from your side, so I can I'll try to clarify your doubts. Any doubt is there, it is highly welcome for you. So I shall welcome any doubt. Again I am requesting, can I have some doubts, or could you entirely understand everything? Yes?
Which situations are Castellan's theorems applied and which situations strain energy?
And you see, it is very important question he has raised, and I want to tell you that this Castleton theorem is not a theorem applied in particular situation. And truly speaking, Castleton theorem can be applied in general, right? It can be applied to any situation. Ordinarily, we are apply a Castleton theorem at a point to find the deflection where the load is applied. But the same situation may not prevail any time. Sometimes you require the deflection at a particular point. For example, you see, suppose this is a cantilever beam, A and B, and length is L. Here another point C is here, it is L by 2 and L by 2. But here load P is applied. But I require, what is that? Deflection at B. That means this will deflect like that. And this is nothing but your delta C. This is nothing but what is your delta B. And I don't require, it is not asked in the problem to find what is the amount of deflection at point C. But it is asked rather at the pre-end. But where there is no point load is there. But ordinarily it seems to be that your Castleton theorem cannot be applied. But remember that it also can be applied there. But only thing you have to introduce a what? A dummy load. A dotted line is not a real load, it is a imaginary load. This is your dummy load. Then delta value is nothing but your dou U by dou W, not by dou P. Right? And if your delta C is required, remember that there is no need for you to introduce dummy load. And here delta U is equal to dou U by dou P only. You see the difference. So dummy load is only be introduced when there is no presence of any point load at a point where deflection is desired. So by this way, I think accelerator can be extended to any situation. So it is applied in general, not in particular situation. Any more confusion is there? Any more confusion? Okay, thank you all for having a beautiful